Recording is rolling. Welcome to Monday. So we're going to kick off with a Kahoot. You guys remember last week went over energy and conservation of energy. So this will be a good review for that. Coming back into this week, good review of energy and work. Then chapter 11 puzzle. So you guys might remember yesterday or last week, I gave you guys a page that says chapter 10 on one side, energy, work, simple machines, and chapter 11 conservation of energy on the other side. We finished all the chapter 10 questions, so today we'll do some of the chapter 11. We'll get most way through that. Okay. You guys remember that page, chapter 10 11 is due this coming Friday, so a few days from now. Okay. There's some other stuff I want to do later this week, including a spring energy lab, but we'll get there when we get there. Okay. But there is one more thing I have to tell you guys before we get going too far, and that's that I have you guys' next Open Notes take-home quiz. So clipped to the right side of your desk is a page that looks like this. Okay. You guys see this page? It says Energy Quiz Honors. Make sure it says Honors and not AP. So this should be clipped to the right side of your desk. Okay. You guys got that? Okay. So 10 questions, 6 on the front, 4 on the back. This is due 1 week from now, next Monday. Of course, if you finish it early, you can feel free to turn that in early. So that's all right. All right, you guys ready for this Kahoot? And a lot of you guys have already logged in using that pin. I'm going to switch my screen back over. Say present screen to share. Right. Oh yeah, look at all you guys ready to go. Give you guys a few more seconds. Hop in there. Right. Oh, and also, if you want to follow along with a hard copy of the questions, you do have a printout. You guys remember this this energy table packet from last week? Right. If you look on the back side of this packet, there are 20 questions that are printed. They're pretty much the same questions that you guys are about to see here. All right, you guys ready to go? Okay, if you're hopping in a minute late, that pin should be at the bottom of the screen. Right here we go. Work is defined as force times distance. If you push something with a force of newtons for some distance in meters, that will be some number of joules of work that were transferred. Like energy transfer. Olivia, Michael, Eli, Owen, Michaela. If Millie Newton pushes with twice the force for twice the distance, she does how many times the work? Double the force, double the distance. Yeah, this is spooky Kahoot. All right, why would it be 4 times the work? Let me flip my screen back over and show you guys why.
What? You are? I've just logged in and answered one question.
So, you guys remember the last question? You just said work is equal to force times distance, right? Now, it's a dot product that means that only the components in the same direction matter. But, right, suppose you got that aside. Okay. What if this is the old work? And then we're going to do some new work. Call this work new, right? And you double the force and also double the distance. So it's a factor of 2 on each of those variables. Do you guys see that's going to be 2 times 2 is 4 times force distance? Like that. And look at this here. The old work was just plain force times distance. Isn't that exactly that right there? Right? Okay, so the new work is 4 times the old work, isn't it? Right? You guys see that? Right. What if you do this? What if you push with 5 times the force for 5 times the distance? What is the new work? It'd be 25 times, wouldn't it? Because 5 times 5 would be 25, right? You guys see that? Okay. All right. See, present screen to share. All right, so back to Kahoot. We got, Michaela to the top, Bella, Olivia, Carter, Michael. The unit for work is joules. Yeah, because you guys know meters is displacement or distance. Newtons measures force, right, like those spring scales. Joules measures energy, and work is energy transfer, right? And then watts, that's power, like work per time. All right, Michael, Kaden, Emily, Eli, Olivia. Power is defined as work divided by time, right? Remember, power is a rate of work, rate of energy, work divided by time. Right? That'd be joules per second, which is watts, right? Work per time. All right, Olivia to the top. Michael, Kaden, Trisha, Emily. The unit for power is watts. Right? So my classic go-to example for power in watts is always just look at the top of a light bulb. If it says 40 watts, that means it's pulling 40 joules per second off the grid, right? That's the rate of energy, rate of work. Joules per second, that's watts. Right, Olivia, hold on to that lead. The amount of potential energy possessed by an elevated object is equal to the work done lifting it. Okay, so a couple of perspectives on this. First of all, it's the only even possible right answer because, the amount of potential energy. Guys, what's the unit for potential energy? Joules, right? Work is also measured in joules. But power, that's watts, force is in newtons, and distance is in meters. Right? Okay, but that aside, why would this specifically be true anyway, besides the units? Right? The work done lifting something is equal to the potential, the energy that it ends up with. Right? Well, suppose you have like maybe there's a crate with some mass, and you're going to lift this crate up to some height. There's like a height change, right? And it's in some gravity field G. Right? Well, that means that this crate would have a weight equal to mg, wouldn't it? Which means that the force to lift it, let's say make a quick free body diagram. Right? If it has weight mg, then wouldn't you have to apply a lifting force, call it F lift, that's at least equal to the weight of the box, like pulling it up, right? Then the work done lifting it would be the lifting force, which is mg, times the distance moved, which is the height. Oh, look at that. The work done lifting it is equal to the potential energy that it's going to end up with at the end, right? Because you put that much energy into it. Michael Cohen on fire. Olivia, Catherine, Emily. Kinetic energy is equal to one half mv squared. You guys know that from, well, there's a poster in the front room that has that listed out. Oh, speaking of posters, I don't know if you guys noticed, but this one on the far end here, well, made that one over the weekend. That's a better replacement poster than one I had before anyway. So, there's also one of your quiz questions. You guys see that very last poster that I just brought in today? Is also one of your quiz questions. The one with the spring in the loop. All right, so 1/2 mv squared, kinetic energy. All right, Michael still holding on to the lead. Cohen's still on fire. How much farther will a car traveling 100 kilometers per hour skid compared to one going at 50 kilometers per hour? That's to say, if you double your speed, what happens to your stopping distance? Double the speed, the stopping distance. It would be 4 times as far. Right. got 4 times the stopping distance. Switch back over and show you guys why. Now this one we did talk about last week a bit. Paper here. Do you guys remember? I got it right here. You guys remember this energy table? The one with the car skidding to a stop? You guys remember that? No, the direct question on the table is what's the final speed, which is obviously 0, but stop. But I asked a side question is, how's that stopping distance relate to the initial speed? Okay, so remind you guys how that works. So if, and so we've got a road, there's a car, with some mass, some V naught initial speed, and the guy slams on the brakes, comes to a stop after some distance d. Okay. Right, so how's that distance relate to the speed? Now, there's a couple of approaches you could take. The old way is you could do, go through, do second law of motion, figure out the rate the car slows down, that's acceleration, then go through kinematic motion, you'll get some answer. But there's a newer, faster way going through conservation of energy. It looks like this. The sum of energy initial equals the sum of energy final. Okay. As long as you have a closed system. Now I'm going to modify this a little bit and say that if the system is open, say that you're only focused on the car, then the initial energy, maybe plus the work done on it, or maybe we should say minus work done by friction if it's negative work, see what you end up with. So the car starts off with all kinetic energy, that's this type. Okay. The work done by friction is the friction force multiplied by the distance, and we're interested in something to do with distance, so if we have that. Then the car itself as an open system would end up with 0 joules of energy at the end, because 0 kinetic energy is not a motion, 0 potential energy, I don't see any hills, I don't see any springs. Okay. Right, so I'm going to do one little algebra step here. Slide over the work term. So whatever initial kinetic energy that car had, well, it's all going to be eaten up by work done by friction. Of course, it doesn't disappear from the universe. It turns into like thermal energy, something like that. But let's look at the relationship between the initial speed of the car and the distance. Now, that Kahoot question you guys just saw said, supposedly if you double the initial speed, the distance quadruples. Well, why does that play out? Okay. Well, if you throw a factor of 2 on that speed, that would double the speed, right? Doesn't that factor of 2 also get squared? Right? Which means the car has how many times kinetic energy that it initially had? 2 squared is 4. That'd be 4 times the kinetic energy, wouldn't it? Right? And then where's that energy go? Well, the friction force itself doesn't change. That depends on the mass of the car and the coefficient of friction. So that factor of 4 all gets routed into the distance. You see that? What if you do this? What if you have 5 times the initial speed? So you go from 10 to 50 miles an hour. 5 times the speed. That'd be what times the stopping distance? What's the factor of 5 squared? 25. Right. Let me do one more thing before I switch back over. There was a trick I showed you guys. You can just make up numbers. What if you had a little toy car that was like 2 kilograms and it was moved at 1 meter per second? And let's say the friction force worked out to be like 1 Newton. Right? What would its stopping distance have to be? Yeah, you guys see 1 meter? That's the only number that completes that equation. Right? So then you go back and you say, let me do it 5 times. Right? What if you did 5 times the speed? You really wind up that toy car. Now it's going 5 meters per second. Okay? Do you guys see there's 25 joules to go around? Okay? And if the friction force doesn't change, then what's the stopping distance? I see it would be 25 meters. Right? So if you're ever not sure exactly how relationships work with just variables, you can always just make up some numbers because it works in general for variables. It should work for any specific solution that you come up with. Right? Like that set of numbers. All right, back to Kahoot. Yeah. So double the speed, 4 times the stopping distance. Got Michael, Cohen on fire, Kaden, Olivia, Trisha. Oh. An arrow in a bow has 70 joules of potential energy. How much kinetic energy will it have after it's been shot? Yeah, 70 joules. This is just conservation of energy. This is maybe all the energy was in the bowstring, like sort of think of it like spring potential. Right. What if it all goes into the motion of the arrow? There you go. Conservation of energy. All right, Cohen, do the top spot. as the pendulum swings back and forth. Okay, yeah. So you guys remember pendulum swinging back and forth? At its lowest point, it's moving really fast, so it has a kinetic energy. And if you define that as height zero, then it's all kinetic. Then at the end points, it's not moving. So, but it is elevated to get up there, so it has all potential, and it just oscillates back and forth. Paul Hewitt did a demo on that too. If you want to go catch that video. But when a car's speed triples, its kinetic energy does what? Yeah, it increases by a factor of 9. Okay. Let me switch my screen over and show this one to you guys. So, you guys remember kinetic energy is 1/2 mv squared. Okay. So if you triple that speed, doesn't a factor of 3 also get squared? And 3 squared would be 9 times. Okay. I'm gonna do my number example. Okay. So what if you had a 2 kilogram toy car and it was moving at 1 meter per second? How many joules of kinetic energy would that be? You guys see 1 joule? Right? Okay. And then what if you go back and speed that car up? That same 2 kilogram car to like 3 meters per second. You triple its speed. How many joules is that? 9 joules. Okay. Maybe possibly you put a force on it to speed it up to that point. You had to do 9 joules of work. Well, yeah. 8 joules of work to speed it up to that point. Yeah, so 3 times the speed translates to 9 times the mechanical energy, or kinetic energy. All right, Cohen's on fire. Trisha, second. Caden, Michael, Olivia, rounding out the top 5. One job is done slowly. An identical job is done quickly. Like same number of joules, identical number of joules. Those jobs require different amounts of what? Oops. That's screen 2. Yeah, power. So, it's the same amount of work. You have to read into this a little bit. Identical, but they mean like the same work, like the same number of joules. So that would also, you'd have to expend the same amount of energy. So the energy would be equal. Okay? But if you do something quickly, you guys remember power is work divided by time? In fact, if you do something quickly, does that require more or less power by doing it quickly? It would be more power, wouldn't it? Right? Because if you divide by a smaller time interval for a faster job, yeah, it'd be like more wattage. Right? If you divide by a smaller number, that blows up the fraction bigger. Right? Yeah, more watts to do it faster. All right, ooh, Cohen extending his lead, still on fire. Which requires more work? Lifting a 70 kilogram sack up 2 meters, or lifting a sack with half the mass up twice the distance? Yeah, same work, same work. Okay. Let me flip over and show you guys this for class. So suppose we got this sack of some mass m, right? It's in some gravity field g, and we're lifting this, and we're gonna lift this and put it on a shelf. Big old bag of money, that's what it looks like. Some height h. So the work you need to lift it, well, you need to apply a force upward, maybe equal to its weight if you're lifting it with constant speed. Okay. You're lifting at some height h. There's force times distance. Yeah, it's also the potential energy it ends up with on the shelf, isn't it? On gh. Okay, so maybe that's the initial work. I'll call it work not. Then there's going to be some new work. So completely new scenario. I got a sack with, what was it? Half the mass. So half the mass of the original one. Same gravity field, but we're looking at twice the height. Right? Do you guys see that the 1/2 and the 2 are going to cancel out? That leaves you with just MGH again. So the same as the original, right? So half the mass, therefore half the weight, right? Twice the height. Those two effects cancel. You need the same number of joules to lift it. Same energy input, same work input. Right there. All right, Cohen, still on fire. Ooh, Carter hopping in there. An object that has kinetic energy must have. I'm sorry, I can't.
You're doing so good. There's no way.
Yeah, I'm sorry.
Just not.
So yeah, momentum. All right. Now, momentum we haven't talked about yet. I pulled these questions out of actually Paul Hewitt materials, and he teaches momentum before all this stuff. So that's why this one got here. But take a look at the ingredients that make up each of these concepts. You guys know kinetic energy, that's 1/2 mv squared. So the ingredients that go to make that up are like mass and speed, right? Mass, velocity. Okay. Now, actually, the next topic we'll talk about is going to be momentum, which is mass times velocity. You guys see it has like the same component parts. Okay. When we do eventually get to this, momentum is a vector quantity versus energy is a scalar, so that's a little bit different. Okay. Turns out the momentum is conserved, similar to how energy is conserved. So that's something to look for in the future. Does something have to be accelerating to have kinetic energy? Does it have to be speeding up or slowing down? No. Or changing its direction? No. Okay. Does it need a force to maintain it? Guys, Voyager 1 spacecraft, isn't it just like coasting? It's been coasting since the 1970s, just going through deep space. Does it have a mass? Yes. Does it have speed? Yes. Does it have kinetic energy? Yes. Does it have momentum? Yes. Is there any force on it keeping it going? Nope. Just inertia, right? All right, got Cohen, Trisha, Carter on fire, Kaden, Catherine. A pulley system can. Yeah. All right, so you guys know, sorry, the blue one. You guys know the pulley system can give you a mechanical advantage. Let's say that whatever your input force is, you can lift something that's much heavier, so multiply your force. Of course, you can also change the direction of the string or the rope and change the direction of the force, so that's all fine again. You could pull down and lift something up, for example. The yellow one is just both those together, so sort of both of both. Now, if you take the red one, I guess you could sort of make a case for that in the sense that you could say, well, if you couldn't lift it originally, but you can with the pulley system, now you can do something where you couldn't before. But in a sort of definition type context, work is like energy or transfer of energy. You can't amplify the amount of energy. Right? So a pulley system can amplify your strength, but it can't amplify the amount of energy, right? Because that would break conservation of energy. Okay, so sort of. All right. Emily, hopping in, top 5. How many joules of work are done to push a box 25 newtons for 3 meters? Yeah, force times distance. There you go. Nice. 25 times 3. Okay. Cohen, still on 5, still in the lead. How much power to do 40 joules of work in 5 seconds? Yep, 8 watts. So you guys know power is work per time. So 40 joules divided by 5 seconds. 8 watts. How much work to lift a 30 Newton crate 2 meters? $60 joules, right? Force times distance, right? Weight times height. 60 joules, 30 newtons times 2 meters. Got Cohen, Carter, Trisha, Kaden, Emily. How much power to lift a 60 Newton crate 10 meters all in 2 seconds? 300 watts. No, why 300 watts? Well, let's go through this. So you guys know power is work divided by time. Well, how much work was actually done on this crate? 600 joules, right? There were 600 joules of work done lifting the crate. Okay. And then since power is work divided by time, take 600 joules, divide by 2 seconds, right? You can see it's going to give you 300 watts. Okay. So force times distance divided by time. Cohen, Carter, Trisha, Kaden, Emily. Last question. She puts out 200 watts of power for every 1,000 watts input. What's the efficiency? Okay, 20%. Oh, look at you guys go. 20%. Yeah, so just divide those two. I gave you guys a different definition of efficiency last week. I think it's real divided by ideal mechanical advantage, but this is consistent with that. So there you go. With the bronze, Trisha. With the silver, Carter. And the gold. With the Cohen. All right, nice job. Runners up, Kaden and Emily. Hey. All right, so flip back over. All right, take a look at these chapter 11 problems, conservation of energy. All right, so last week we did all the chapter 10s, so up to chapter 11. Looks like this. The first one we're doing, number 57. We got Tony. Tony has a mass of 45 kilograms, is moving with a speed of 10 meters per second. Okay. Got a few questions about that. Find his kinetic energy. Suppose the speed changes. Now what's his kinetic energy? And then later on, what's the ratio of those kinetic energies? You know what? Actually, let's look ahead a little bit, because this is one of those proportional type questions. Guess his original speed was 10 meters per second, and later on it's 5 meters per second. So it's half the speed, right? Because if you have half the speed, what kinetic energy do you have compared to the original? And it's not half, it's 1/4, right? That actually is going to be the answer to part C. But we'll do that the long, slow way and show that that's the case. We'll get numbers to the joules and take the ratio. But you guys know the answer to C even before we start. So number 57, zoom out. There we go. So Tony has still mass. I'm going to do what I normally do, change the numbers a little bit. I'm going to make this guy 60 kilograms and give him a speed of, let's say 12 meters per second, something like that. Okay. All right, so part A, what is his kinetic energy? Well, that's your 1/2 mv squared, which is 1/2 at 60 kg times 12 meters per second, n squared. 1/2 times 60 times 12 squared. Okay. Looking at 4,000 and something joules of kinetic energy. Okay. That's part A. Part B says, what if you cut his speed in half? So I know I'm using different numbers from the book, but call it K and K and B. Okay. I'll also cut the speed in half, so leave his mass the same. Okay. I'm going to cut his speed down to 6 meters per second, which is half of my original speed. Okay. Wonder how many joules this is. So 1/2 times mass times speed squared. Okay. I'm looking at this many joules, 1,000 and something joules. Okay. There's part A and part B. Okay. Of course, a little bit different numbers from the book. Okay. And part C says, what is the ratio of kinetic energies in part A to part B? Okay. Let me do this both ways. Ka over Kb, and then later on Kb over Ka, so that if you have a certain preferred way of thinking about this, the original to the new versus the new to the original. Okay. So the first way of thinking about it would be 4,000 and something joules compared to 1,000 and something joules. Okay. Wouldn't that be a 4-to-1 ratio? Okay. 4 times? Okay. And the new way of doing it is just that upside down, which is 1/4. Okay, so by cutting his speed in half, he has 1/4 of the original kinetic energy. Okay. Yes, sir? All good? You guys ready for next one? Okay, number 60. A car. Oh, hey, car brakes. Hey, you guys saw this in Kahoot, and you guys also saw this last week. So suppose you got this car. Notice they gave you the weight of the car, not the mass. Okay, so that might be important later. We'll find out. It's traveling at this speed. Right? The brakes are applied and the car slides to a stop, as shown in this figure. The average braking force between the tires and the road is so many newtons. How far will the car slide when the brakes are applied? Okay. How far will the car slide? This is number 60. Let's see. I'll do here. They gave you the weight of the car, right? And I'm gonna make up my own numbers. I'm gonna have a 19,000 Newton car. Right. They gave you the initial speed of the car. I'm gonna call mine say 35 meters per second. Right. And one more thing, they told you the friction force. The friction force is I'm gonna make mine say 12,000 newtons, like that. Okay. How far will this car go braking to a stop? Okay. So there's it's good. We have the speed, friction force. Okay, we'll be able to make use of that too. Okay. But what's a probably more directly useful value for the car? Its weight or its mass? I'm thinking it's mass, right? Because if we're thinking about like 1/2 mv squared to get the kinetic energy of the car. Okay. Can anybody look at this and tell me what the mass of the car has to be? You guys remember how weight is mg? I've been using mg for weight all along the semester, haven't I? Okay. And so if you have some number of kilograms of mass, you just multiply by 10 meters per second squared to get the weight in newtons. Okay. Well, if you have the weight in newtons, shouldn't you just divide by g to get the mass? Okay, guess that. So how many kilograms is this car? 1900. Of course, that's my notes numbers, not the book numbers. Okay, you guys get that? Okay. That's the number we're going to make use of. So let me set up the conservation of energy. Sum of energy initial, leave a space there, equals sum of energy final. That's true for a closed system. If it's an open system, I'll say minus the work done by friction, so it can come to a complete stop. And so we start off with some 1/2 mv squared minus friction force times distance goes to 0 joules of energy at the end. So it comes to complete stop, no kinetic energy, no hills, no potential energy, no springs. Okay, then what's the question? It says how far will the car slide? So this distance d. Okay. Let me do one more rearrangement, and then we'll plug in some numbers. So whatever kinetic energy it started off with, it's all going to translate into work done by friction, which will tell you how far car slides. All right, let's plug in some numbers. So I need the mass of the car. Oh, yep, that's why we went and got that mass, that some number of kilograms for the car. Okay. Moving at the original speed of this many meters per second, and don't forget to square the speed. That's an important part. Okay, okay, they told us the friction force, so that's nice. This many newtons of friction force for some distance. Right. Is that right? Okay, so it looks like there's only one algebra step, and that's to divide both sides by 12,000 newtons. Divide both sides by 12,000 newtons. Let's see that. Right. So what is all this stuff? What is 1/2 times 1900 kilograms times 35 meters per second being squared? I'll divide by 12,000 newtons. I'm looking at a stopping distance of 96.98 meters, call it 97 meters. 97 meters is my car's stopping distance. Woo! That's about length of a football field right there. Which also makes me wonder, I wonder what the coefficient of friction is. Now, the book doesn't ask that. That's my own side question. But do you guys think you could solve for the coefficient of friction? You guys remember what coefficient of friction is? Side note over here. You guys remember that's friction force compared to normal force? You guys remember that? Let's see what's going on with that car. I should draw a picture. Car, let's say it's moving to the right. We usually have movement to the right. Read English left to right. It moves to the right. On some road. Quick free-body diagram. So this car has a weight, mg. This car has a normal force, which is equivalent to the weight. And then there's a friction force, F sub FR. And the coefficient of friction, you guys remember, is friction force compared to normal force? Okay. So the friction force, that was given. And the normal force, well, that would be equivalent to the weight as long as it's a level road. And the weight was given. So isn't it just 12 divided by 19? You said? So let's see what my coefficient of friction is. Coefficient of friction, and it would be kinetic friction because sliding. Well, actually, no, that's not necessarily true. I guess if this car had anti-lock braking system, it could be static. So let's call it generic coefficient of friction. What is 12,000 divided by 19,000? That is 0.63. All right, it's like a pretty realistic number. Okay, you guys good there? Okay, number 61. A cart with this mass is moving with this velocity down a level hallway. Okay, a constant force of so many newtons acts on the cart, and its velocity becomes slower. So, guys, did you guys know that the cart slows down? Which means that the force is acting which way compared to the velocity? In the same direction or in the opposite direction? It has to be the opposite, right? That's why it slowed down. Okay. What is the change in kinetic energy of the cart? How much work was done on the cart? And how far did the cart move while the force acted? Let's find out. This is number 61. Right. I think I want a whole picture with this one. There. So we got the ground right here. Let's get ourselves a cart. Some little cart wheels. And was initially moving, say V naught equals, okay, here's where I'm going to make up my own numbers that are pretty close to the book numbers. I'm going to say 9.0 meters per second. But then later on, let's say this car is only moving at, let's say, V final is like 2.0 meters per second. Just to come up with some numbers. They told you the mass of the cart. Put that. Maybe down here. Mass of the cart is, I'm going to say 17 kilograms. Okay. And I'll have a friction force, or just some kind of backwards force. It might be a friction, I don't know. Right. Say 11 newtons. 11 Newton backward force. Okay. Now, of course, this car also has a weight and a normal force. Right, those exist too. mg, F sub n. Right. Okay, there's the free body diagram. Okay. All right, now, first question, what is the change in kinetic energy of the cart going from here to here? Since this is energy conservation chapter, try to stick to the energy conservation approach. So kinetic energy initial is equal to whatever the original 1/2 mv squared is. That would be 1/2 times mass of the cart is 17 kilograms, times the initial speed of the cart was 9 meters per second, being squared. So 1/2 times 17 times 9 squared. I'm looking at 688.5 joules of energy. Kinetic energy, final, in second scenario, 1/2 times the same 17 kilograms times only 2 meters per second being squared. Right, so here's the 2. I'm looking at 34 joules of kinetic energy. Okay, so the change in kinetic energy, this is part A. Okay. So part A says, what is the change in kinetic energy? And I'm going to represent it as delta K. Delta K means change in kinetic energy. Okay, change in kinetic energy, delta K. Okay. That's K final minus K initial, which is 34 joules minus 688 something joules. Okay, what is 34 minus 688? 5. Okay. I'm looking at negative 600 and something joules of, okay, that's the change. Okay. And of course it would be negative because it ends up with fewer joules than it started with. So change has to be negative. Okay. And final minus initial. Okay. Is that right? Okay, good. The second question, how much work was done on the cart? How much work? Well, this is a work energy theorem question, because isn't it true that this force applied for this distance is the work done on it, and that work is going to be the change in kinetic energy of the cart? Because again, I don't see any hills, so none of the energy goes into the potential energy. I mean, I don't see any springs either. Okay? So this answer right here, part A, is also the answer to part B. That's A and B. So work energy theorem, whatever the change in kinetic energy is, right, if there's no elevation change, right, must also be the work done on it. So A and B have the same answer. Is that okay? Part C, how far did the cart move during this whole process? How far? Okay. So that would be this distance here to here. Oh, it's this distance D. Okay. What is that distance? You know what? I know that work is force times distance. And I know the force because, well, the book gave it to you, so I made up a number also. And I know the work. So if this work is this force times some distance, then can you just solve for distance? One more thing. The fact that the cart is moving forward, if I want my distance to be positive, like forward is positive, then actually the fact that this force is going backwards, shouldn't I actually call this negative? Okay, so when I go plug in a number, so I should call it like negative so many newtons. Right. So we're going to do that. So the fact that you know the change in kinetic energy, right, and the fact that it's the same thing as work, I'm going to finish off like this. Work is equal to force times distance. The work done is just this number. So negative 600 and something joules. And the force, I wrote as this number, and your book has some force on the cart for some distance. Okay. All right, so what is 654.5, 11? Okay. The negatives cancel, and I'm getting distance is equal to this many meters. Okay. And since my numbers are a little bit different than the books, but they're not that far off, you guys should also get an answer that has the same order of magnitude. Like somewhere, if you get somewhere between like 50 and 100 meters, it's probably pretty good. Okay. Somewhere there. All right, you guys good there? Let's do this, since we just have a few minutes left. I want to show you guys that this is consistent with the old wave doing this, which is go through Newton's second law of motion and then go through kinematic motion. Here, I'll just do this on my calculator. So the old way of doing it was to say, to figure out the distance, was, well, first you have to figure out the acceleration of the cart. And the acceleration is net force divided by mass. So take the force of 11 newtons divided by the mass of the cart, which was 17 kilograms. Let's see, the acceleration, here's the old way. So, old way. Okay. Acceleration equals net force on total mass, which is negative 11 newtons acting on 17 kg, okay, which is negative 0.647 meters per second squared. Okay. Then you kick that back to kinematic motion, say final velocity squared equals initial velocity squared plus 2ax. Where final velocity was given as 2, initial velocity is 9 meters per second. So it's going to 2 meters per second, don't forget to square that. From 9 meters per second, don't forget to square that. And then acceleration is negative 0.647 meters per second squared times some value x. Now this value x should be 59.5 meters. Let's see if it is. So it's 2 squared minus 9 squared. That's negative 77. All right, divide by 2 times negative 0.647. Okay, moment of truth. When I hit enter, my calculator screen should say, well, it might be using rounded numbers slightly different, but basically 59.5. Let's see if it is. X equals 59.5, 59.5 meters. There you go. So we are all good. All right, that is a good pause point for today.